Hi everyone. Once again, it is Professor Deborah Oakley here at the University of Nevada, Las Vegas School of Architecture. I want to thank my many subscribers for joining me here. Although I make these videos mostly for my own students at the School of Architecture, I know that there are a lot of viewers here from literally all over the world, and so I thank you for your patronage. And today I'm going to go over very basic linear equilibrium problems, and I'll do these both graphically and analytically. So hopefully this can get you started working with graphic analysis and trigonometric analysis of simple vector equilibrium problems. So let's get started. Alright, so our configuration here is a support bracket which is carrying 10,000 pounds, 10 kips, has two elements, a horizontal element and a sloping diagonal element at 45 degrees, a one-to-one slope. And what we want to do is analyze this structure for the internal forces. We'll start off by doing this graphically and then look at it also analytically with trigonometry and linear equilibrium. So for beginning students, what I strongly advise everybody to do is to really understand this conceptually before you even do any calculations. What I mean by that is to take a section of this. We'll look at the free body diagram of this top joint here. And so that is our 10 kips here. We have a sloping member at 45 degrees and a horizontal member here. By applying our equations of linear equilibrium, some of the forces x equal to 0, some of the forces y equal to 0. We can see, even without any calculations, that we have to have a balance of the 10 kips in the vertical force, vertical direction, and there's no place for that to go other than the vertical component of this sloping member. The horizontal member cannot carry the 10 kips because it's not a sloping element. So we apply the vertical equilibrium first, and we see that negative 10 kips plus, we'll call this py equals 0. So py is the one that has to go up. And because I have a py, I also have a px. Anytime you have a sloping member, always think about breaking it down into its components. So now that I have a horizontal px by sum of the forces in the x direction equal to 0, this is sometimes written as sum of the forces in the y direction. I did say v here, didn't I? So y and try that again. V equals 0. This means the same thing. Sum of the forces vertical equals 0, sum of the forces y equals 0, sum of the forces x equal to 0, or sum of the forces horizontally equals 0. They mean the same thing. So we have a px here. If px is going to the right, point my pen that way, px is going to the right, I have to have a force going to the left, and the only place that can be balanced is in this top member t. So that's minus t equals 0, t equals px, and it has to go into the left direction. So we haven't really done any numeric analysis, but we see that there's an equilibrium in the horizontal and vertical direction. So that's a conceptual understanding that you should always do. Now we'll do the graphic analysis. We're working with two diagrams in a graphic analysis. The first is the original diagram. We call this the form diagram. And this does not necessarily need to be drawn to any scale. Notice that there are no dimensions on here. What's really important in this configuration is just the geometry, which is an interesting aspect of doing triangular analysis. So the form diagram can be at any scale. This is not really to any particular scale. It is proportional, though. We work that in conjunction with our second diagram called the force polygon. That is drawn to a scale. So that means that every distance measurement on here corresponds to the magnitude of a force. So I want to find something that's big enough to draw my elements without being so big it goes off the page, or without being so small that it maybe doesn't quite give us the accuracy we need. For this one, I can see that if I use a scale of 1 inch is 40, that gives us this distance here for 10 kips. So this would be 1 inch is 400 pounds in this case. So I draw my vectors corresponding to the magnitude and direction that they are in the diagram here. So I start off with 10 kips. So that's measured 10 kips on my 1 to 40 scale. And this is the beginning of my force polygon. So again, this is at a scale of 1 to 40 in this case. So the nice thing about triangles are that given the length of one side and any of the internal angles, we know everything else. And so what we're trying to determine is the length of the vectors that are representing the forces in these members. So we are given their angles, and all we have to do is construct a polygon based off the initial known force of 10 kips. So I like to use a rolling ruler to do this. We'll start with the horizontal line here, and we're going to form a closed polygon that is around the tip to tail, tail to tip of your applied load. So we start off with our horizontal force. That's the line of action of that force. And as you know, the line of action represents an infinite line that passes through whatever member we're talking about. The force is applied anywhere along that line, either as a push or a pull by the principle of transmissibility. Our other line comes from this diagonal, and that's going to connect our tip. And we've now constructed a force polygon. Our magnitudes are measured right from this diagram. So our horizontal force comes out to 10 kips. And our sloping force comes out to about, looks like about 14.2 kips. Now, from this analysis, we can already tell that this is going to be a compression member, meaning it's pointing back towards the joint. So let's just heavy this up a little bit to remind ourselves that this is taking all the compression force. And the other member pulling away, that has to be tension. Well, let's see this in the diagram here. If I connect from tail to tip, tip to tail, go around the circle here, that means I'm going up this direction on the sloping member. Relative to this joint, we're pointing up there, so indeed this is a compression member. Here we go from the tip of this member to the tail of the next member. Relative to this joint, again working back and forth between these two diagrams, we go from here to here. It's pulling away, therefore it is a tension member. That is what we analyzed up here conceptually. Now, the nice thing about a graphic analysis is that we can very quickly determine the effects of changes in the force system. So let's consider making the angle, instead of 45 degrees, let's make it 30 degrees. So I've already got this marked off with the protractor here, is 30 degrees. So I'm going to draw a line here at 30 degrees, and we'll see what's the effect of this. Do the forces stay the same? Do they go up? Do they go down? Well, one thing does stay the same. That's the 10 kips, and its direction is down because that's our applied load. So our vectors still make the same basic pattern. Their intersection point is simply going to be different. So our force T is horizontal here. That doesn't really change. The line of action is the same. I'm going to point that over here. Our second vector, the sloping one, still comes from this point, but instead of going at 45 degrees, as I said, this is a 30-degree angle here. So we're going to grab that angle off of the form diagram and carry it down. And now our force polygon looks like this. And you can visually see how much longer this line is than this one. And if we scale this up, we're coming up with about, looks like all the way to 20, not quite 21, we'll call it about 20 kips. And horizontally, we're getting about 18 kips. And that's in tension again, and this is compression. So didn't write here, this is tension. So the senses of the members, the direction that they apply, do not change, but the magnitudes change substantially. So what if we do another change? What if instead of putting this at 30 degrees, we make the angle 60 degrees? So I'll do this in a blue pen, or pencil really. So I've got a mark here at 60 degrees. That will be my new angle. So it becomes much deeper. Again, the 10 kips, that stays the same. The only thing that changes, the horizontal is still horizontal, but the sloping member has changed. So I'm going to grab the angle off of this and pull it back. And look at that. Look how much shorter that is and how much lower the forces are. So we get the magnitudes by scaling. And here we have, it looks like about 11.5 kips. It'll stay in compression because go around the circle here, this arrow is still going to be pointing from the tip of that one going up and then back again, the same. So 11.5 kips compression on the vertical or sloping member, and a little bit less than 6, about 5.9 kips in tension. So that's one of the great advantages of graphic analysis, is that we can see the effect of changes visually without any mathematics very quickly, and the calculation for the size is very quick. This is a procedure that was used for, well, over 100 years. Fantastic structures like the Eiffel Tower were designed basing on graphic analysis techniques. My other videos show that in more detail. So that's the graphic analysis procedure. Let's do the same thing. This time we'll do trigonometric analysis. This is still linear equilibrium, but it's by mathematics. So we've already started it right here. It's involving our equations of linear equilibrium, but it's actually solving for the forces. So let's do the bracket at 45 degrees like it was at the beginning. So 45 degrees, sum of the forces in the y direction equal to 0. We have negative 10 kips plus py equals 0. Therefore, py is 10 kips. The relationship of the forces internally, which is to say the x and y components relative to one another, depend on the angle. So in this case we have a 1-to-1 ratio. Py, we've said, is going to be 10 kips. Then we have px. By ratio, px is to py as 1 is to 1, our slope here. So very simply on this, px is 1 times py, or px equals py. So px also equals 10 kips. To get the true force P, we'll use the Pythagorean theorem in this case. That says that P is going to be equal to the square root of the sum of the squares, px squared plus py squared. That equals square root of 10 kips squared plus 10 kips squared. So that's P is the square root of 200. That should kind of look familiar to. It's basically the square root of 2 times 100. So P comes out to 200. And see if I can get the shadow off of that. Take the square root, 14.1 kips. That is the true force in the sloping member. Now that's our sum of the forces in the y direction equal to 0. If we do sum of the forces in the x direction equal to 0, we started that here. We said t equals px. That's pretty darn simple. So t is going to be equal to 10 kips. So that's the mathematical analysis of the structure. Now, what if we do, let's say we take the 60-degree angle here. I didn't mark that on here, but this is internally angle. Here is 60 degrees. Let's do that steeper angle. And how does that work out on our calculations? Now, one thing about the analytic process is that we don't actually have to draw things to scale because we just need the numeric values for these. So I'm going to draw that piece of free body diagram again, 10 kips down. We have a horizontal element here and a sloping element, and this is at 60 degrees. I still want my components though. So I've got py and px and our value of t here. So here's the interesting thing to start with. If I sum forces in the y direction equal to 0, it's going to look exactly like this because I have negative 10 kips going down plus py going up equal to 0. Py is still 10 kips. That's because the only place that the vertical force can go in this situation is into the vertical component of this member P. And so it's always going to be 10 kips, even when it slopes at various angles. And we see that right here in the graphic diagram. The vertical line not only is the applied force here, but as this is drawn, this is also the vertical component, Py, of the sloping force. Similarly, this is the horizontal component, Px, of the the horizontal force. So embedded into this graphic diagram are those components. We can read those directly. So now let's construct the geometry of this. So we have 60 degrees here, P, Py, Px. So we have our 10 kips here. Now I want to get both the T and the Py. Many textbooks will go directly to the P and sum it directly, which I think is a little more confusing than keeping it in its components before you get the final answer. So let's do it that way. We know Py, that's 10 kips. We want to find Px. So we get that not by sum of the forces horizontally yet, but we get that by the geometry of this situation here. And we know that the tangent of 60 degrees in this case is the opposite, 10 kips, Py over the adjacent Px. So Px is going to be Py divided by the tangent of 60 degrees. So that's 10 kips And we get the tangent of 60 degrees. Which is 1.73. So I'm going to take that 1.73, divide that into 10. I get 5.77 kips. That's our value of px. Our value of p, now we would use the cosine of 60 degrees because it will be the adjacent over the hypotenuse. So that is going to be, let's start with the trigonometric value itself. Cosine of 60 degrees is going to be px over p. Now I'm solving for p here. That's what I'm interested in here ultimately. So that means that p is going to be px divided by the cosine of 60 degrees. We solve for that, 5.77 kips. And we divide that by cosine of 60, which is 0.5. Therefore, p comes out to 11.6 kips. Well, I'll write the whole thing, 11.55 kips. And now by linear equilibrium, in the x direction, I'll write that over here, sum of the forces x equal to 0. Well, we already know that p to the right, that this force here, px minus t equals 0, so px always equals t in this situation, so t equals 11.55 kips, and it is going to the left in tension, away from that joint. We can also find this value of p by the Pythagorean theorem, since we already knew the value of py, px is 5.77 kips. So we could say, or p equals the square root, again, the square root of the sum of the squares. So 10 kips squared plus 5.77 kips squared. So 5.77 squared is 33.29. 10 squared is obviously 100. Add that together, so that's p is the square root of 133.29 kips. P equals 11.55. So that corroborates what we did right there. So I'd like to take this one step further here and show you the value. This is the algebraic analysis, trigonometric analysis. I'd like to show you the value of the graphic analysis method versus the algebraic analysis when you have a more complex situation. And we can make our bracket slightly more complicated. Let's even go back to the 45 degrees here. We've got our 10 kips being applied right here. But let's make it a little more interesting. What if we tilt the bracket? What then? Well, here's the thing about this in terms of the trig analysis. So we started out saying that we've got a vertical component and a horizontal. Now things are different. Now the top member no longer is unable to carry a vertical force. It actually has a sloping component. So we have, in fact, another set of components. So we've introduced a level of complexity here. We'd say sum of the forces in the y direction are equal to 0. We have negative 10 kips. This is our px, py, tx, ty, negative 10 kips plus py, but we also have minus ty. So we cannot solve that directly for the equation. We also have to have some of the forces x equal to 0. And what we know from that is that px minus tx equals 0, or px equals tx. So that relationship is not changed, but what's changed is that the 10 kips is shared between the bracket bottom and the top. This involves a simultaneous equation solution. It's perfectly doable. I'm not going to do it here. I'm sure there are many YouTube videos that show that, but it's a much more involved process by doing it in using trigonometry. Graphically, it is absolutely no more difficult. So I'm going to go to my 1 to 40 scale. There's my 10 kips. And this is at 1 to 40 again. I'll construct this exactly as I did before. I'll take my sloping vector here, and now I'll take my top vector. This is no longer horizontal, and I'm going to run into my calculations here just to illustrate the principle. And that is the graphic solution. So let's see how the forces have changed. So this is still 1 to 1. I have no idea, that was an arbitrary angle there. If I measure this, I get about 23 and a half kips. Still in compression. Follow those arrows around in a circle. It's going upward, it's pointing back towards my joint. This one pulls away, again in tension, and this is about 18 kips. Now compare that to our first solution, and we see a dramatic increase. We had 14.2 kips, it's gone up to 23 kips simply by dropping that element down. But we see that the process of creating this force polygon is absolutely just as easy in this situation as this situation. However, the algebraic analysis gets more complicated because we have to do simultaneous equations. Again, I'm not going to do that here. If you are interested, you can look that up on some other videos. That, in a nutshell, is the basic process for graphic and trigonometric analysis for a vector force system. Hope that's helpful. Thank you.